Hello everyone, I am Rishikesh Patil, a third year student from Computer Engineering branch, and today we'll be discussing about the gradient descent algorithm concept for finding the best fit line equation. So we'll begin with the today's video, the best fit line, and we'll understand the linear regression and optimization. We'll measure the best for the residuals. At the heart of finding the best fit line lies a fundamental concept of residues. Residues, or we can call it as errors. A residual is the vertical distance between an actual data point and the predicted data point of our candidate line. These distances represents that how far from the prediction and from how far till the reality. The quality of a line's fit is determined by the magnitude of these residuals. As we have mentioned the magnitude, it means that the smaller the residual, the better the line fits, which means that the residual must be as small as possible. If it is as small as possible, then the line will be fit the better way. And vice versa, if the residuals is large, it will be a very poor prediction. The very large the residuals, the prediction would be way too poor. If the residuals are small, we are capturing the underlying pattern effectively. Now we'll imagine it with an example. Say for example, we are taking multiple lines and we are overlaid on our data. Each would produce different set of residuals, different set of residuals. And our final goal is to find the one that minimizes these overall errors. So now we'll move forward and we'll talk about the regression equation. We know that the equation of line is given by y equals to mx plus c, where y is the on the y-axis, m is the slope of the line, and c is the intercept on made on the y-axis. As we keep on changing the value of slope and the intercept, we'll get many lines. If we keep on changing the intercepts, the slope, will get infinitely many lines. And this is where the challenge itself is. We must find the specific value. If we can't find, then we'll get many lines. So as I have mentioned in the challenges itself, that we have to find a specific value of the slope and the intercept that enables this line to bestly predict the y and x across all our data points. Different values of m and c create different lines, as I have already mentioned. So we need an optimal combination. So now we'll move forward. The loss function, measuring total error. As we can see here, we have stated a formula of MSE. What is MSE? MSE is mean squared error. This formula is 1 upon n into summation of actual minus prediction whole square. The MSE, that is mean squared error, we calculate the average of the squared residuals across all data points. Now we have to evaluate and how well a line will fit in our data. So we need a single number that captures the total error. So we might be thinking that why we do square. After doing square, the error will be increased, right? So no, that's not the case. After squaring, it basically serves two purposes. The first is that it eliminates the negative values, so errors cannot cancel out. The second is we penalizes the large errors more heavily. So that's why we are squaring it. A single prediction that's way off and it contributes more to MSE than many small errors combined together. So for a given line, we can calculate its MSE, that is mean squared errors, and our final goal is to find a line with the smallest possible MSE. As we have mentioned previously, as we can see here, the smaller the residual, the better the line fits the data. And now we'll discuss about the optimization problem. We face a well-defined optimization challenge and we have to minimize the loss function, that is MSE, as I have mentioned just now. And we have already discussed that the equation of line is given by y equals to mx plus c. As we keep on changing the value of slope and the intercept, we'll get infinitely many lines. And this is it. The parameter space is vast. Infinite possible combinations of slope and intercept exist, but only one combination, and it will minimize the total error. So for that, we'll look upon two concepts, that is small data sets and is large or complex data sets. So firstly, we'll talk about small data sets, which is of the closed form. The solution exists. We can calculate optimal value of slope and intercept directly using the matrix concept in mathematics. And the second is large or complex data. We use iterative method. Iterative method is we keep on repeating the same thing, and this iterative method becomes very necessary because we search for the minimum by taking steps towards it. Iterative approaches are particularly valuable in modern ML algorithms where datasets are enormous. There are various datasets, and closed form solutions becomes computationally prohibitive. So this was about the optimization problem. Now we'll move forward to the concept of gradient. In gradient, we use a concept of partial derivatives. I'll explain partial derivatives in a very simple example. Suppose we have a function of x and y. Say for example, we are having a mathematical equation as z equals x square plus 2y. As the equation consists of x and y, so when we do partial derivative with respect to x, we have to take y as a constant term, a constant. So as I have taken the example as x square plus 2y, if we are doing the partial derivative with respect to x, the solution of x square will be 2x, and we are keeping 2y as a whole as a constant. So the derivative of a constant will be 0. So the solution will be 2x itself. And vice versa, if we take difference partial derivative with respect to y, this we have to treat x as constant. So the example that we have taken is x square plus 2y. So x square is a constant term, so its differentiation will be 0. The differentiation of 2y will be only 2 because differentiation of y will be. So this was about partial derivatives, and using this partial derivatives we'll be able to calculate what actually gradient is. As I have already mentioned that we use iterative methods. So here again, iteratively find the minimum of our loss function, we need directional guidance. So here comes the concept of gradient, which is a mathematical compass showing us which way we have to move. So as I have already mentioned about the partial derivatives, and we have already mentioned that if we keep on taking different slopes and different intercepts, we'll get different lines. And the gradient is a vector quantity and it contains partial derivatives of the loss function with respect to the each parameter, that is slope and the intercept. If we talk about a small crux from all this, at this current position, which direction causes the error to increase most steeply? So here comes three main concepts, that is gradient point uphill, uphill, upside. We move downhill to the downside. And the third is convergence. Convergence means if there are two lines, the two lines come together, that is they are converging. So we'll talk about gradient points uphill. It basically indicates the steepest direction of error increase. The steep, if there is, suppose there is an increase and then there is sudden increase, this is a steep. We move downhill. Downhill move, this means that we minimizes the error. That means we are moving in opposite direction of the gradient. And finally, about the convergence, eventually we reach the bottom where the gradient is 0. So this was about the concept of gradient. We have calculated it using partial derivatives. And now we'll move forward to the gradient descent process. Gradient descent is an iterative algorithm, as we have seen earlier itself about the iterative algorithm, that we keep on repeating the same thing that systematically finds the optimal parameter. And now we'll discuss that how basically it works. At the first, we initialize it. That is, we start with random guesses for m and c. As we have seen the equation of line y equals to mx plus c, we are having unknown two values, that is the slope m and the intercept c. So we are starting it with some random guesses for slope and intercept. Now we'll calculate the gradient using that MSE formula, which was 1 upon n times summation actual minus predicted whole square, and with respect to the values of m and c. Now we'll move forward. That is, the values of m and c, will move them by a very small step to the gradient direction. And finally, we'll repeat the process. As we have already mentioned in the beginning, that gradient descent is an iterative algorithm. That is, we keep on repeating the things iteratively. We'll do this for 2 to 3 times until conversions. And finally, when the loss stops improving meaningfully. So this was about the gradient descent process. Through repeated iterations, we descend the error landscape until we find the value, the point of minimum error. So now we'll move forward to the key concepts of this algorithm. So basically there are three key concepts. That is, the first is the learning rate, the second is iteration, and the third is convergence criteria. Gradient descent behavior depends on three critical parameters. As I have mentioned, the first is learning rate, second is iteration, third is convergence criteria. Learning rate controls step size in each iteration. Iterations is the number of updates cycle performed, and convergence criteria is the stopping condition where it stops when the loss function or parameter becomes negligibly small. So this was about the three basic key algorithms which are very much important, and these concepts make gradient descents computationally efficient even for massive data sets. When we are working with massive data sets, it becomes very much important, and for complex models with thousands of parameters. So this was about the three key concepts of the algorithm. Now we'll move forward for the why gradient descent over closed form, as we have given a clear cut difference between why we choose closed form solutions over gradient descent. Because closed form solution requires metric inversion, but in gradient descent the scale efficiently with data size. It basically handles complex and non-linear models. This is not the case with closed form solution. It works only for linear problems, whereas gradient descent works for the foundation of deep learning. As the data and the model grows more complex, the gradient descent becomes not just preferable, it also becomes essential. And this is why it's the backbone of entire neural network, that is deep learning, virtually all the modern ML algorithms. So this is the reason behind choosing closed form solution over gradient descent. And now we'll move forward to the final part of the presentation, that is from data points to the best line fit. As we have already seen in the beginning of this video, that the less the error, the best will be the line fit. And we have covered the journey of the entire linear regression optimization. We have seen the loss function, gradient descent, best line fit, data points. And the key takeaway is only that the best line emerges not through magic but through the formula, mathematical formula, as we have seen various formulas in this video. So we minimize the residual errors using gradient descent to iteratively find the optimal parameters. This elegant process enables accurate predictions and form the foundation of modern ML. So now, using this, we'll be able to analyze and understand this concept in a more better way. So this was all about the gradient descent concept. I hope you have understood it. Thank you.